So we have some important properties related to the geometry of the cross product. So the first thing is that u cross square v is orthogonal to both u and v. So we have seen that in the last example. And of course, assume that u and v are non-zero vectors in 3 dimensions, so 3-dimensional vectors. Then the following properties are true. U cross square v is orthogonal to both u and v. Now, for the second property, we define the angle between the two vectors. Let's say theta is the angle between u and v. Then you have some other way to calculate the angle of between the two vectors in addition to the formula that you see in the dot product. So let's say the angle theta between u and v is given by. So you have the magnitude of u crosses with v equal to the magnitude of u times the magnitude of v times sine of the angle theta. Again, theta is the angle between u and v. And here, again, you have a different formula to calculate the angle between the two vectors. Another formula that can help you calculate the angle between the two vectors is the one you see in the dot product. So you have cosine of theta equal to the dot product u dotted with v divided by the magnitude of u times the magnitude of v. So you have now 2 different ways to calculate the angle between the two vectors. So I'm not going to derive this formula, so I'm just going to give you the formula and we can work with that. But I will relate this formula back to the area of parallelogram. Now, in the case that the two vectors are parallel to one another, u and v are parallel if and only if u crosses with v give you the 0 vectors. Okay. And one last property is that u, v, u crosses with v form a right-hand rule. Alright, so these are some of the properties that you may encounter when you calculate the cross product. So the first one you have seen the example. The second one we're going to derive this formula, but in relations to the area of parallelogram. The third one is for you to check if the two vectors are parallel or not. So this is a different way to allow you to calculate that. Right? In the dot product, you can calculate the angle between the two vectors, but they have a different approach on how would you integrate the result of the dot product. Right? Again, let me go back to the dot product here. So this is the geometric interpretations of the dot product. So it depends on the dot product. You can have a different type of angles. You can have an acute angle. You can have an obtuse angle. The angle can be 90 degrees. The angle can be 0 degree, and the angle can be 180 degree. So again, in this case, you have a different way to calculate the angle and also use that to identify if the two vectors are parallel to one another or not. Now, for the last property is form a right-hand rule. I don't know if you can see my hand, but this is the right-hand rule. Right? So this is the two vectors, and this one, my thumb, is going to form a cross product. So this cross product is going to be orthogonal to both my index finger and the middle finger. All right, so that is the geometric properties of the cross product. Now I'm going to relate the second property to the area of parallelograms. Okay, so I'm going to do let u and v be the adjacent side of a parallelogram. So you have that right here. Right? So you have a parallelogram here, and the two sides going to be can be formed using vector u and a vector v. So the area of the parallelogram so the area is equal to the base times height. So now we're going to calculate this area based on the information that we got based on the information of the vector u and the information of the vector v. Alright, so the base of the parallelogram is the magnitude of the vector u. where base is equal to the magnitude of vector u, and the height can be calculated as so it takes a little bit of trigonometry to derive this height. Okay, so the angle between the two vectors u and v is going to be theta. Now I want to calculate the height of the parallelograms. It turned out this height is also the height or one of the side of the right triangle here. So this is the right triangle I'm talking about. So to calculate this side, you can say that sine of theta is equal to the opposite. That's what you're looking for, which is the height, divided by the hypotenuse. Okay, so the opposite side of the right triangle, right here, is the height that we are looking for. Now the hypotenuse is the magnitude of the vector v. Okay, so the magnitude of the vector v, and therefore to calculate the height, you cross multiply v, the magnitude of v, with sine of theta. So you get the magnitude of v times sine of theta. Okay. And therefore the area is equal to the magnitude of u times the magnitude of v times sine of theta. And that is the area of parallelogram. Right? And it's related back to the magnitude of the cross product between u and v. And therefore, to calculate the area of parallelogram, and the parallelogram is formed using the two vectors u and v, therefore the area can be calculated as the magnitude of u crosses v. Right. So it's straightforward calculations, not too difficult. Hopefully you can see the derivations, you know where's the formula coming from, and why we calculate the area of parallelogram using the magnitude of the cross product between u and v. Now consider the following example. So I would like to find the area of parallelogram formed by the points P1, P2, and P3. All right. And as you can see, this is the parallelogram that we are considering right now, and the side of the parallelograms formed by the two vectors, the vectors P1, P2, and the vector P1, P3. So I could calculate first the two vectors P1, P2, and the vector P1, P3. So calculate P1, P2. So P1 is the initial point, P2 is the terminal point. And so you got -1 minus 2, comma 0, minus 2, comma 2, minus 0. So this gives me -3, -2, 2. Now for the vector P1, P3, P1 is the initial point, P3 is the terminal point. So you got 0, minus 2, 4, minus 2, 3, minus 0. And this gives me -2, 2, 3. And to calculate the area of the parallelograms, we do so the area of the parallelogram formed by P1, P2 and P1, P3 is the magnitude of P1, P2 crosses with P1, P3. Okay, so I'm going to carry out calculations for the cross product. That means I'm going to apply the determinant approach here. That is P1, P2 vector crosses with vector P1, P3. So you have a 3 by 3 determinant. The first row is ijk, the second row is the entry of P1, P2, which is -3, -2, 2. And the last row is for the entries of P1, P3. So -2, 2, 3. So this is equal to I hat times -2, 2, 2, 3. Minus j hat times the determinant of -3, 2, -2, 3. Plus k hat times the determinant of -3, -2, -2, 2. So for the first component, you have a 2 by 2 determinant. So I hat is equal to -2 times 3 minus 2 times 2 minus j hat times -3 times 3 minus -2 times 2. And the last component is of k hat. You have -3 times 2 minus -2 times -2. So the first component again give you -6 minus 4. The second component, j hat, give you -9 plus 4 plus k hat. And the last component is -6 minus 4. And so you got -10i plus 5j minus 10k. So this is the cross product between the two vectors p1, p2 and p1, p3. And if you take the magnitude of this resultant vector, you're going to have the area of parallelogram. So the area of the parallelogram is the magnitude of p1, p2 crosses with p1, p3, or the area is equal to square root of. So take the sum of each component square. So -10 square plus 5 square plus -10 square again. And if we do the calculations correctly, it's supposed to be square root of 225 or 15 for the answer. So the unit in this case is going to be unit square because we are calculating the area. Now another thing that you can do is that if you divide the result by half, you can actually calculate the area of the triangle here. So this is the triangle we're looking for. So another way, in addition to what we already calculated, we can calculate the area of the triangle formed by P1, P2, and P3. The area is going to be, so area is equal to 1/2 the magnitude of P1, P2 crosses with P1, P3, or 1/2 times 15, right? And again, this is the unit square. So this is one of the geometric representations of the cross product. So it's help you calculate the area of parallelograms formed by the two vectors. Alright, so for me, that's it for me in terms of the cross product. We're going to stop right here and I'm going to move on to lecture 14 when we talk about vector space.